Subaru Telescope uncovers ancient fossil in the outer solar system. Imagine uncovering a relic from the very dawn of our solar system, an untouched time capsule drifting at the edge of the sun's reach. That's exactly what astronomers have just accomplished, and the implications could rewrite what we thought we knew about our cosmic neighborhood. But here's where things get controversial. This discovery could challenge one of astronomy's hottest debates about the mysterious so-called Planet 9. Using the powerful Subaru Telescope, a team of international astronomers recently detected a tiny, distant object beyond Pluto. This celestial body, catalogued as 2023 KQ-14, was first spotted during 3 separate observing sessions in March, May, and August of 2023. The find is part of the fossil formation of the outer solar system, an icy legacy project, which leverages the Subaru Telescope's remarkably broad view of the sky to hunt for these incredibly faint and remote objects. After its initial discovery, researchers spent months piecing together 2023 KQ-14's journey through painstaking follow-up work. In July 2024, they gathered additional data with the Canada-France-Hawaii telescope and scoured older astronomical records, effectively tracking its path for nearly 2 decades. This deeper look revealed something extraordinary. 2023 KQ-14's orbit is so far-flung and unusual that astronomers have categorized it as a sednoid, joining only a tiny club of 3 other known objects in this class. Notably, sednoids reside in a region of space almost untouched by the gravity of Neptune, hinting at a much more intricate outer solar system than textbooks have told us. Now, here's the part most people miss. Extensive computer modeling, run by the fossil team using cutting-edge resources from the National Astronomical Observatory of Japan, suggests 2023 KQ-14 has remained in its stable orbital track for an astonishing 4.5 billion years. That's nearly the age of the solar system itself. Intriguingly, simulations show that although today's sednoids follow different paths, about 4.2 billion years ago, their orbits were strikingly alike. What could have divided them? Dr. Yuquan Huang, who led the orbital simulation study, weighs in on the controversy. Because 2023 KQ-14 now strays from the pattern set by other sednoids, it makes the popular Planet 9 hypothesis look less probable. Perhaps a massive, long-gone planet, the ghost of the solar system, once played a role, only to be knocked away in a cosmic game of billiards. And this is where scientists start to disagree. For years, Planet 9 has captured imaginations, a hidden giant thought to lurk unseen, sculpting the orbits of far-flung ice worlds. But if 2023 KQ-14 and its sibling sednoids are so different, is Planet 9 even real? Or are these orbits the scarred echoes of ancient cataclysms? What do you think? Hidden planet or missing planet? Dr. Fumi Yoshida, another key researcher, emphasizes the importance. Finding 2023 KQ-14 way out in a region where even Neptune barely exerts influence means that something out of the ordinary must have happened in the early solar system. The existence of these stretched-out orbits and huge distances from the Sun challenges our understanding. Unlocking the secrets of these rare objects gives us crucial clues about the solar system's history and violent past. Yoshida adds, the Subaru Telescope is one of the few tools on Earth that can make discoveries like this. Each new find gets us closer to telling the full story of our planetary origins. So, as astronomers continue to comb the outer frontiers, and perhaps find more cosmic fossils, the puzzle of our solar system's past only grows more fascinating. Do these discoveries reshape your view of the solar system? Should astronomers keep searching for Planet 9, or is it time for new theories? Let's hear your thoughts below. Do you agree with the researchers' conclusions, or do you think something even more extraordinary is waiting to be discovered? Unveiling Ammonite, discovery of a new Sedna-like object. Unveiling the secrets of a Sedna-like object with a perihelion of 66.0. Abstract. Trans-Neptunian objects, TNOs, that possess significant perihelion distances, q greater than 60O, and semi-major axes, a greater than 200O, are pivotal in enhancing our understanding of the early solar system's evolution and the potential existence of a distant, yet-to-be-discovered planet. Observing these celestial bodies is notoriously difficult, leading to their infrequent detection. However, they are essential for refining models of solar system formation. In this study, we present the discovery of a Sedna-like TNO, designated 2023 KQ14 and affectionately named Ammonite, which has a perihelion of 66O, a semi-major axis of 252O, and an inclination of 11 degrees. Notably, Ammonite's orbit diverges from those of other Sedna-like objects, effectively bridging the previously identified Q-gap in the distribution of distant solar system bodies. Our simulations indicate that Ammonite maintains dynamic stability over a timescale of 4.5 billion years, JR. Furthermore, our findings imply that Ammonite, along with other Sedna-like objects, may have originated from a shared primordial orbital clustering approximately 4.2 billion years ago. Additionally, the stable orbit of Ammonite suggests a preference for larger orbits, around 500O, for a significant hypothetical planet in the current Trans-Neptunian region. Main. The initial discovery of Sedna has sparked a lively discussion regarding the formation and evolution of the far reaches of our solar system. Typically, TNOs exhibit perihelia of less than 40O, with their trajectories heavily influenced by the gravitational pull of Neptune. In contrast, Sedna-like objects, characterized by their extensive semi-major axes, greater than 200O, and large perihelia, over 60O, seem to follow stable orbits that have remained largely unchanged since the solar system's inception, unaffected by Neptune's gravity. Currently, there are no effective mechanisms to elevate their perihelia given the existing planetary configuration, indicating that an external gravitational force beyond the known planets is necessary to account for their orbits. Various hypotheses have been proposed to elucidate the orbits of Sedna-like objects. 1. Interactions with a rogue planet-sized body or a solar mass star. 2. Gravitational interactions with a hypothetical distant planet. 3. Solar migration within the Milky Way. 4. Stellar encounters that occurred while the Sun was part of its original star cluster. 5. The capture of interstellar objects from low-mass stars during the solar system's early development. Currently, only 3 Sedna-like objects have been identified, leaving this group poorly understood. The challenge of discovering additional objects is compounded by their significant distance from the Sun, which results in very faint apparent magnitudes. Expanding the catalog of Sedna-like objects is crucial for deepening our understanding of the solar system's history, and for placing more stringent constraints on the aforementioned hypotheses. Phase 2 of the formation of the outer solar system, an icy legacy project, Fossil 2, builds upon the original Fossil I initiative, utilizing the 8.2M Subaru Telescope located on Mauna Kea. Fossil I employed a long-term observational strategy, repeating observations across 2 to 5 locations to capture light curves of solar system objects. Fossil 2 aims to survey approximately 25 square degrees to a limiting magnitude of is asymptotically equal to 25.2, concentrating on 2 main objectives: 1. Detecting high perihelion TNOs and 2. Classifying the dynamics and size distribution of resonant TNOs. This project builds on earlier, shallower surveys such as the Canada, France Ecliptic Plane Survey, the Outer Solar System Origin Survey, and the Dark Energy Survey, with the goal of enhancing the inventory of small and distant outer solar system objects, thereby facilitating improved population modeling and property exploration. In the first year of Fossil 2 observations, we identified the object 2023 KQ14, nicknamed Ammonite, notable for its exceptionally high perihelion. the barycentric orbit fit, derived from a 10.16-year observation arc, utilizing both our data and archival information, in the J2000.0 reference frame, reveals parameters of A equals 251.9 plus or minus 0.30, E equals 0.7383 plus or minus 0.0003, I equals 10.98 degrees. With an error of less than 0.01 degrees, omega equals 72.104 plus or minus 0.001 degrees, omega equals 198.71 plus or minus 0.03 degrees, and Q equals 65.9 plus or minus 0.20. With a heliocentric distance of approximately 71.00 at the time of discovery, May 16.5, 2023, Universal Time. With a perihelion of 66.0, Ammonite ranks third in perihelion size among TNOs listed by the International Astronomical Union Minor Planet Center, following 2012 VP113, 80.60, and Sedna, 76.30, and preceding Leliakuanua, 65.00, 2021 RR205, 55.60, and 2013 SY99, 50.00. The median magnitude of Mr. equals 24.6 corresponds to a diameter range of 220 to 380 kilometers, depending on albedo values of P equals 0.15 to 0.05. This discovery fills the perihelion gap in TNO findings between 50.0 and 75.0, underscoring the significance of identifying distant TNOs to better understand the structure of the far solar system. Interestingly, Ammonite's perihelion longitude is oriented oppositely to that of other Sedna-like objects. Its elevated perihelion hints at the possibility of long-term orbital stability, making it a valuable candidate for testing recent theories regarding the primordial clustering of Sedna-like objects and the existence of a distant massive planet by analyzing its orbital characteristics and overall dynamical behavior. Results: the parameters A and Q that define Sedna-like characteristics can vary, especially concerning long-term orbital stability over 4.5 gyre. Dynamical studies indicate that some objects with similar large Q values, such as 2013 SY99 and 2021 RR205, may undergo gradual orbital migration or diffusion due to minor perturbations from Neptune and the influence of galactic tides or passing stars. While objects with large semi-major axes and Q greater than 45.0 generally remain unaffected by the giant planets, their long-term stability must be confirmed through numerical integration. One potential method for analytically defining the current diffusion boundary is to apply the resonance overlap criterion, which distinguishes between chaotic and non-chaotic regions in a Q space. Ammonite's semi-major axis is comparable to that of the hypothetical planet proposed by Badijan and Brown, as well as to the boundary of Neptunian mean motion resonances, where an object may experience perihelion raising through von Zeipel, Litov, Kozai dynamics, or mean motion resonances. Furthermore, Ammonite serves as an excellent test case for the primordial clustering of Sedna-like objects generated by a transient planetary body. Consequently, we conducted numerical simulations to verify Ammonite's orbital evolution. Long-term stability. Both forward and backward simulations using two independent codes indicate similar stability, with mean variations in the semi-major axis and eccentricity remaining below 1% for the best fit, highest, and lowest orbits. The inclination of Ammonite's clones fluctuates between 8 degrees and 11 degrees throughout the simulations. None of the 1,000 clones exhibited signs of resonant behavior in their orbital history. The nearest major resonance, the 24:1 at A equals 250.10, is approximately 5 sigma away from the rare fossil object Ammonite discovered at the edge of the solar system. Get ready for a mind-bending journey to the edge of our solar system. Astronomers have just unveiled a remarkable discovery, a celestial fossil that's sparking both excitement and controversy. Meet Ammonite, a nickname inspired by the ancient fossilized mollusk, which has been found lurking on the outskirts of our solar system. This intriguing object, formerly known as 2023 KQ-14, was detected by the Subaru Telescope in Hawaii, as revealed in a recent paper published in Nature Astronomy. But here's where it gets controversial. Ammonite's orbit and location suggest an extraordinary event from our solar system's ancient past. Fumi Yoshida, a planetary scientist at the National Astronomical Observatory of Japan, NOJ, explains that Ammonite's orbit is so distant that Neptune's gravity has little influence on it. Ammonite is the fourth sednoid ever discovered, a technical term for objects with unique orbits in this far-flung region. The presence of these objects hints at an ancient mystery, Yoshida says. Understanding their orbits and physical properties is key to unlocking the full story of our solar system's history. And this is the part most people miss. Ammonite's orbit has remained stable for at least 4.5 billion years, yet it differs from the other known sednoids. This diversity in the outer solar system challenges our previous understanding. The discovery of Ammonite also reignites the debate about Planet 9, a hypothetical ninth planet in our solar system. Some astronomers suggest that Planet 9's gravitational influence could explain the orbits of distant objects like Ammonite. However, Yukun Huang, an astronomer at NOJ, argues that Ammonite's orbit doesn't align with this hypothesis. It's possible a planet once existed but was ejected, leading to the unusual orbits we observe today, Huang explains. Ammonite was found as part of the Fossil Survey project, which aims to uncover the icy legacy of the outer solar system's formation. While a more classical name will be assigned later, the Subaru Telescope's role in this discovery highlights its unique capabilities. I'm excited for the fossil team to continue uncovering these ancient secrets and piece together the complete history of our solar system, Yoshida adds. So what do you think? Does the discovery of Ammonite support or challenge the Planet 9 hypothesis? Let's discuss in the comments and explore the mysteries of our cosmic backyard.